Hello, good morning. Today we will see the Michelson-Morley experiment. This experiment was carried out by Albert Michelson and Morley in 1887. The aim of experiment was to just prove that whether the medium ether exists or not. Now, what is ether? Ether is the hypothetical medium. Hypothetical in the sense, uh, in those days, we know that the light is a electromagnetic wave, and as sound waves or say water waves need material medium for the propagation of that waves. In a similar way, as light is a electromagnetic wave, we must need a medium which is present everywhere so that light can propagate through that medium. So it was thought that there is a certain medium like say ether which is present everywhere including vacuum so that light can propagate through that medium. So the verification was given by the Michelson Morley. The experiment was carried out in uh, 1887. Okay, so Michelson Morley experiment. So let us see the introduction. What is the background of the experiment? I have already explained. Luminiferous ether, we can say. Experiment method requirements that we will discuss, and we will discuss the result of the experiment. Okay. So as I told, Michelson-Morley experiment was a scientific experiment to find the presence and properties of a substance called a ether. The experiment was done by Albert Michelson and Edward Morley in 1887. Since waves in water need something to move in and sound waves do as well in air, it was believed that light also needed something to move in. Scientists in the 18th century named his substance a ether. So they believed that ether was all around us and that it also filled the vacuum of space. Michelson and Morley created this experiment to try and prove the theory that ether existed. They did this with a device called interferometer. So what is luminiferous ether? As I told, Earth is luminiferous ether medium is present everywhere, and as Earth is moving around say several kilometer per hour, okay, Earth is revolving around the sun with speed say with several kilometers per hour around the sun. If ether exists, then the relative motion of Earth with respect to ether, so that will be counted. Okay, so that is a ether wind, we can say. uh, Ether should seem like a moving substance with respect to earth, to things on the earth. Okay, so for the requirements for the experiment, we require a light source which is monochromatic source, a glass plate, two mirrors we require, mirror M1 and mirror M2, a telescope to observe the fringes, and a compensating glass plate we need. Okay. So the Michelson interferometer that we have studied in the last year syllabus. Okay. We just try to find out the uh, path difference between the two rays. Okay. Uh, we don't go details of the experimental arrangement. Okay, we directly discuss the experiment. So here this is the coherent source of light. Coherent source of light means monochromatic source of light. Generally we use the sodium vapor lamp. Generally we use the sodium vapor lamp as a coherent source of light. So light ray falls on the glass plate. Now this is the semi silvered glass plate. This is semi silvered glass plate. Semi silvered means it partly reflects and partly transmits the light. Okay, now this is the semi silvered glass plate kept at an angle 45 degree with the horizontal, so that if horizontal ray falls on the glass plate, semi silvered glass plate, the reflected ray will go to the mirror 1. Okay, so this will be perpendicular, and the remaining portion, that is transmitted ray, will move towards the mirror M2. Okay, now as this reflected ray and this transmitted ray, as they are derived from one single ray, so they are the coherent sources. So these are the coherent sources, so which is the important condition for the interference. Now after reflection from the mirror M1, this is the reflection from mirror M2, and both these rays, reflected ray and transmitted ray, both these rays interfere with each other, and we can observe the interference pattern through the telescope, that is a detector. So here circular fringes can be observed from the telescope here. Okay, so interference pattern, sometimes it is circular, because when it is circular, because the mirrors M1 and mirror M2, they are exactly perpendicular to each other. Okay, so this is the condition. If you just slightly change the angle of this mirror M2, then the circular fringes may be converted into the straight fringes. So this is the optics part, we don't discuss here. So we are just concentrating on the circular fringes, where these mirrors are exactly perpendicular to each other. Okay, now as the apparatus is moving, because earth is moving with a speed, what is the speed of earth? Speed of earth is several kilometer per hour. Okay, now as earth is moving, as when these rays are separated here, so as earth is moving, the ray will reach this place. Okay, otherwise if it is not moving, this will travel perpendicular like this, but as the earth is moving, it will travel like this, and it will come back like this. As the apparatus is moving, the path of the ray should be like this. Okay, then now when both rays interfere with each other, we'll observe the circular fringes as shown in the first slide. Okay, now here in this diagram, the compensating glass plate is not shown in the diagram. Okay, what happens? This one ray is, this reflected ray is traveling through by this distance, and it is crossing this glass plate two times. Okay, and this transmitted ray is like coming in this way, and it is going like this. Okay, now to compensate the path difference, we need a compensating glass plate, which is not shown in the diagram. Okay, now let us calculate the path difference between these two rays. This is reflected ray and this is transmitted ray. And the one important thing it is that the distance OA and distance OB is same, that is equal to L. Okay, so in the diagram it is not shown exactly equal, but the OA, distance OA and distance OB is same, and that is equal to say L. So let us calculate the path difference. Okay, let us see the details of this experiment, that is Michelson interferometer experiment. Okay, so these are the fringes that can be observed through this detector. So these are the circular fringes. Circular fringes can be observed when these mirrors are exactly perpendicular to each other. So this is the schematic diagram of Michelson interferometer. So as the apparatus moves, so this is the monochromatic source of light. Light ray is coming like this, it is going like this. Okay, but as the apparatus is moving, so it will reach this place a dash. A will be moved to a dash when the ray reaches here. Okay, so this dotted line shows the projected position of the mirror M1, okay, due to the motion of earth. And after reflection from mirror B2, okay, so B also will move to B dash, and after reflection from B dash, they both rays are interfere with each other here, and we can see the circular fringes where the detector is kept to observe the fringes. Okay, so this is a horizontal position, and this is the vertical position. So what we are doing is we will calculate the path difference. We calculate the length of the path here, and we calculate the length of path here. Okay, and we calculate the length of path, and we calculate the path difference, and then we estimate the phase difference, or say path difference creates any shift in fringes or not. That is what we are going to see. Okay, now to calculate the path of this ray, we just carry out the vector calculus. So this is the velocity of light c, and this is the horizontal motion, say v. Okay, so resultant path can be easily calculated by using the simple vector calculus. Okay, and here, as the apparatus is moving, or say the earth is moving with velocity v, and along this direction, this is the velocity c. Okay, so if both are in the same direction, moving in the same direction, the velocity will be added. As a simple logic, velocity will be added if the ray of light and the motion of earth is in the same direction. And while coming back, the ray of light is moving in opposite to that of the motion of earth, so there the velocity will be c minus v. While going, it is c plus v, and while coming back, it is c minus v. So let us calculate the time required to travel this distance. Okay, and time required to travel this distance. Okay, so that one can calculate the path difference. So here the total time taken by the transmitted wave, say OB plus BO, like this, as I shown, it is OB and say BO. As I let it say B dash O, like this. Okay, this O will reach this position O dash, and while going it is say O B dash, and again P dash into O dash, like say. So we calculate the path, the time required to travel this path. Okay, so that will be equal to what? It is simply t2 is, say, t2 is the time required to travel this distance, is equal to, say, L upon c plus v. While going, as I told you, the velocity will be added as they are in the same direction, and while coming back, the velocity will be c minus v, because they are in opposite direction. Okay, so the length will be same, that is say L. While coming or going, the length of path will be same, that is say L, and therefore total time t2 will be equal to L upon c plus v plus L upon c minus v, is equal to twice L upon c into 1 minus v square by c square. Okay, so this is the horizontal path traveled by the light ray. Now the total time taken by the reflected wave, as I said, this is the vertical motion of sorry, vertical direction. Okay, so that is say O A dash and A dash O. So that will be calculated by simple vector calculus. So that will be is equal to T1 is equal to L upon under root of c square minus v square plus L upon under root of c square minus v square. So it is going like this and coming back like this. The time taken will be same, and that is equal to L upon under root of c square minus v square. So if you draw the simple vector triangle, you can have this formula easily. Okay, so the time required to travel this distance is equal to, say, t1 is equal to 2L upon c under root of 1 minus v square by c square. Now this t1 and t2 are not equal. T1 and T2 are not equal. That means there should be certain phase difference. Time difference creates phase difference, and phase difference creates path difference. Okay, so let us calculate the time difference first. So time difference is equal to delta t is equal to, and that can be equal to, say if you solve this, we will get 2L upon C into 1 upon under root 1 minus V square by C square minus 1 upon under root, sorry, not under root, 1 minus, sorry, V square by C square. Okay. Now, if you solve this and simplifying the equations, neglecting the higher powers and so that, okay, so the finally you will get the expression as delta t, that is the time difference between a reflected ray and the transmitted ray to reach the place O is, say, delta t is equal to L into V square upon C cube. Okay, then so you just remember this delta t, that is equal to L into V square by upon C cube. Now, if the whole interferometer is now rotated through 90 degree, that means this horizontal position goes to the vertical side and this vertical position will come to the horizontal side. Okay, like that. When the whole interferometer is rotated through 90 degree, the time difference again will be same, but it will be minus. Okay, so that is equal to delta t dash is equal to minus L V square upon C cube. This time difference will be minus because the horizontal ray will going towards the vertical and this vertical ray is going towards the left side, opposite side. Okay, like that. So therefore the time difference that is denoted by delta t dash is equal to minus L V square upon C cube. Okay, now so the total path, when we rotate through 90 degree, the time difference again, the time difference will be equal to delta t minus delta t dash is equal to twice LV square upon C cube. So the time difference is now increased by rotating the interferometer through 90 degree. So the total time difference will be equal to 2L V square upon C cube. Now effective path difference is equal to velocity of light into time difference, that is delta t. So this is simple formula, distance is equal to velocity into time, like that. Okay, so effective path difference becomes equal to C into 2L V square upon C cube, that will be 2L V square upon C square. So this is the effective path difference. Now if path difference is there, then there should be fringe shift. So as we have studied in optics, if there is a path difference between the two rays, so fringe shift is there. So initial fringe position and final fringe position will be changed, and that fringe shift is equal to effective path difference upon wavelength, and that is equal to 2LV square upon lambda C square, where lambda is the wavelength of monochromatic light we are using. Okay, and if we keep the data, or say if you put the data, that is say L is equal to say 11 meters. So this was the experimental details which was carried out by Michelson and Morley. L was 11 meters. C is velocity of light, that is 3 into 10 to the power 8 meter per second. Lambda wavelength of light is say 5.5 into 10 to the power minus 7 meter, or say 5500 angstrom we can say, and velocity of earth, that is equal to 3 into 10 to the power 4 meter per second. Okay, so if you put this data in the fringe shift formula, the value comes out to be is equal to 0.4. That means when the apparatus is rotated through 90 degree, the fringe positions, the fringes should be shift by factor how much? 0.4. 0.4 times fringe shift should be observed. But practically no fringe shift is observed in the experiment. Theoretically the fringe shift should be 0.4, but practically no fringe shift is observed. That means what? Now the experiment was repeated several times at several different places, but even though no fringe shift is observed in this process, in this experiment. That means what? Our calculations regarding the relative motion of earth with respect to ether medium, or say relative motion of light ray with respect to ether, is not true. Okay, so that is what we are going to see. That is the result. Michelson Morley tried to observe the fringe shift by continuously rotating the interferometer during day and night at different place on the earth, but could not observe any fringe shift. Hence, as there is no fringe shift, the result of the experiment is negative. The experimental result showed that the speed of light is same for all observers, and for the propagation of light in free space, no medium is necessary. That means the concept of ether is discarded by the result of this experiment, and we can say that the speed of light is same in all conditions. So this is the important result, and this experimental result was explained properly by the theory of relativity. By the special theory of relativity, one can explain the result. That is what we are going to see in the next lecture. We will discuss the frame of reference, we will discuss the Galilean transformation equations, and then we see the drawbacks of Galilean transformation equations, and then we will see the Lorentz transformation equations, and later on we'll see how Albert Einstein, how these experimental results were explained by the Albert Einsteins. So that we will see in the next class. Okay, thank you.